All right, welcome everyone. Thank you for joining Mahé Talk. So today we are going to talk about memory and with where all my memory is gone. So today we are trying to map the Kubernetes memory metrics to actual physical resource. I hope you will learn something. So I'm Mahé. I'm working as a software engineer at Isovalent at Cisco. I'm working on Tetragon, which is an eBPF-based runtime security project. It's part of Cilium. And this is not a picture of me. So it all started with something like that for me. So a memory dashboard. So you might end up in the same situation, and I was quite confused at what was the number I was actually looking at. So here you have like an application running, a bunch of pods of this application in your cluster, and they are like consuming an amount of memory. But what is this memory about, and how can I actually understand what is this about? So if you are checking the this dashboard in particular, you might see something like this, and in your case, it might be the same. So the memory metric that is actually used behind the scene is this thing called container memory working set bytes. So it's a pretty long name, and for me, it wasn't very clear what it was about. So let's try to understand where these metrics come from and how it's built. So this is the first conclusion, very early conclusion. I think I could be fairly right to say that the main memory metrics that is tracked in the Kubernetes world for pods is container memory working set bytes. So the thing I wanted to do next is trying to understand where it comes from. So one idea was just to read the documentation. In the documentation on the website, you can see a bunch of description of like the resource metrics pipeline and these kind of things. But one good idea was to look at the Prometheus dashboard itself. So I just wanted to show you how it works. Because Prometheus might be running as part of your cluster, you can just like port forward the service, the Prometheus server, and then you will have access to the dashboard. So I'll try to zoom in. And from the dashboard, you can see a bunch of information, and among which is like the target health. And here you can see that Prometheus is scrapping a various number of endpoints. Here you have like the API server, the nodes, and a bunch of service endpoints. So by gathering all this information, plus a very nice blog post written by a guy named Mahé Tardy, I could kind of create this little diagram of the Kubernetes metrics flow. So I will try to explain the different parts in this graph. So on the left side, you have these green boxes. So those are just services that might be running as part of your cluster of outside, but this is just what we are fetching for Grafana or kubectl top. And you have like this big blue box, which is the abstraction of your nodes. And on this node, you have like a bunch of processes running. Those are the purple boxes. You have kubelet, so this is the one responsible for starting the containers and managing the containers on your node. You have the container runtime, the Prometheus node exporter. So this thing is running as part of a daemon set in the cluster, but it's running on the node and exposing metrics. And as part of the kubelet, you can see you have like a bunch of endpoints. So those are HTTP endpoints exposed via kubelet, exposing various metrics. So in our case, we were looking at this Grafana dashboard for memory, so we are directly reading information from the Prometheus server. You can even like see when you are on your Prometheus instance, you can query the container memory working set bytes directly from here. And you can like graph it and then like see these metrics, right? So this is coming from Prometheus, of course. And the next thing was like, where does Prometheus scrap these metrics from? So there are like two main culprits here, the Prometheus node exporter and the cAdvisor endpoint. So let's start with the Prometheus node exporter. So this thing is a daemon set, as I said. It's running as part of your cluster, and it's running on each node. And because it's running as part of a pod, it is exposed as a service. So if you want to take a look at this thing, you can port forward the service, this one. And with curl, for example, you can query the metrics path and put it into less. So if we do that, we will see a bunch of metrics exposed here, like a bunch of Go-related metrics, but the vast majority of the metrics will start with this node prefix. So this is not really what we are looking for. And if we check for anything starting with container, it won't be there. So this one is mostly about exposing data about the node health. So it's not really about the workloads themselves. Let's get back to the presentation. All right. So the next culprit is the cAdvisor endpoints. So the cAdvisor endpoints, it's something that is running as part of the kubelet, right? It's exposed via the kubelet. So the nice thing is that we can actually read this directly by querying the Kubernetes API. We can use this command. So we can kubectl get and use this very nice proxy feature in the API server. So we can use like /API/v1 nodes. In my case, I have only one node. It's like a locally running cluster. It's Minikube. And then you have like this proxy thingy. And you can pass any endpoint you want to retrieve directly on that node, on the kubelet node, via this proxy thing. And if we check like the thing from the metrics from this endpoint, we can see that now most of those are starting with the container prefix, which is actually what we want and what we are looking for. So let's get back to this. So now we have like one more conclusion. The container memory working set bytes, it comes from cAdvisor inside kubelet. But most of you in the room might actually wonder, like, what is cAdvisor? What is it running inside of kubelet? So let's try to understand that further. So cAdvisor, it's the project on the left. This is basically a utility for you to analyze and understand the resource usage of your containers in a cluster, or just like on the node, sorry. And I wanted to mention runc here because pretty much all the underlying technical implementation of cAdvisor is relying on runc libcontainer, which is the pure Go implementation for interacting with containers on in the Kubernetes world. It's used by containerd, it's used by cryo, etc., etc. So yeah. And how does this work now? Like, how is my container memory working set bytes computed by this cAdvisor thingy? So let's try to make sense of this diagram. It's a pretty big diagram. I will try to walk you through it. So it all starts with this getStat method that is called inside of the cAdvisor code, right? And just after this thing, it calls this cgroup manager getStats. And it calls this getStats that is on the right. So now we are like jumping into runc libcontainers code. And we are executing in the package that is called cgroup. And you can see here that we are trying to retrieve stats from this thing called cgroups. Apparently, they come in two flavors, right? They have like cgroups v1 and cgroups v2. And depending on the version, libcontainer is doing like slightly different things. And you can see at the bottom that we have, for example, different name for similar metrics. It's reading memory usage in bytes for cgroup v1 on one side, and on the other side, it's reading memory current and other statistics. So all these stats are collected thanks to the libcontainer cgroup package and returned to the cAdvisor code. And then eventually, they reach this set memory stats function. And this is the actual function that will produce the metrics we have been looking for since the beginning. So let's take a look at the code. The code, like the simplification, looks like that. It's fairly straightforward in some sense. It's retrieving the usage we've been seeing in the slide before, so usage in byte for v1 and current for v2. And then it's retrieving something else, which is called total inactive file in the case of v1 and inactive files in the case of v2. And then it just does like this subtraction. Very simple code, like the working set is basically the usage minus the inactive file thingy. And we can recap this with that. So it's like kind of the max between 0 and this. It can be negative, of course. Like we can have like negative memory usage, unfortunately. And for v1, we have like memory usage in bytes minus this total inactive file. And for v2, we have current minus inactive file. So, right, great. Now we know that. But we know that cAdvisor computes this metric from this stats from this C group using this current minus inactive file. But what is this things about? Like, what is this current stat about? What is this inactive file about? And what is a C group, right? So here is a wall of text. Please don't read that. It's just like as an illustration purpose. It's the Linux man page for C groups. But what I wanted to explain here is that containers are not like a C group, Linux concept, right? They are not like the OS concept. And for creating containers on the OS, we used various systems like namespaces, C groups, and other systems actually. Namespaces on one side are for like isolating the process with the rest of the computer. Like you can create like a network C group, and the process will have its own vision of the networking. Or you can create like a process C group, and the process will think it's the only one running, plus the other process running inside its container. Well, it's not true. But on the other side, you have like C groups, and C groups are mostly to restrict the usage of resources on the system. So you can have like CPU C groups, so to restrict the CPU usage. So basically the idea is you want to see how much CPU you're using, and maybe you want to restrict, like say, I don't want this process to consume 100% of my CPU. And then you have like the memory C group. So this is the one we are going to be interested in now. And the idea here is to retrieve a number of information from the memory usage on the OS from this C group, and also like enforce memory limits, maximum and minimum. All right. So Kubernetes, they use C groups. Basically, when it's starting a container, it's talking with the kubelet, which is talking to the container runtime, which is creating some cluster. And they have this abstraction of quality of service classes. So you may have never seen this kind of quality of service thing, but you may have interacted with them without knowing, because you have like 3 main service classes: guaranteed, bustable, and best effort. And those are actually related to the way you set limits and requests on your workloads. So when you don't set anything, like most of the time, it's just like best effort. It's going to be like in this category. When you set like one request and a limit that is above the request or no limits, it's going to be in bustable. And if you set a limit that is equal to the request, it will be guaranteed. So Kubernetes uses this concept using the memory limit and request to kind of classify the different workloads. And this will make sense because it will Kubernetes will use this concept of quality of service classes to tune certain settings inside of the C groups. So this is another concept. So the out-of-memory killer, you may be familiar with this one because it may have killed your containers in the past. Again, this is like a Linux concept. This is like an OS concept. It's not aware of containers in this case. And what happens on the system when it cannot reclaim any more memory, it needs to pick one of the process to actually terminate that process and get back some memory. So the whole challenge here is to actually pick the right process. So Kubernetes uses like this quality of service to choose like the score it's going to assign on each of the containers. So the idea being here is that like guaranteed will be a lower score than best effort, and in between will be burstable. And the idea being is that the out-of-memory killer will target a best effort port before a burstable port and before a guaranteed port. Yeah, I just wanted to make a note aside as well to show you like the kind of quirks that can happen between the Kubernetes world and the OS world. Like for example, again, the out-of-memory killer is not really aware of the containers concept. So when it's picking a process to kill, it doesn't know if it's like the main process of a container or not. So you can end up in this weird situation where like the out-of-memory killer is like killing process 2 in your container, and Kubernetes still sees that, or kubelet still sees that the process 1 is running and healthy, so it doesn't do anything. So you can end up in this kind of weird situation. So yeah. Anyway, what we had here is that we use these C groups to kind of classify our containers and to like tune these kind of settings. And How it's actually done in reality, the interface between the OS and the kernel and the user space for cgroups is using a file system. And all the cgroups, they can be represented in this file system thingy. Here we'll use like the systemd terminology with the slice and the scope thingy. And what you see here is that you have like at the very top, you have the root cgroups. So these cgroups contains all the process on your computer. So you will see the statistics about memory from all the process running on your computer, and you can adjust settings on all the process. And then in the case of Kubernetes, you will have like this kubepods thingy. And here you can see why I try to explain this quality of service classes. It's because like they will manifest themselves as categories in the kubepod slice. So you will have like this guaranteed, best effort, and bustable slice. And in each of these slices, you will retrieve all your pods. So I picked best effort in my case, and I put like 2 pods. And you have like pod on the left and pod on the right. And the pod on the left, I added like much more details. And you can see the container, like the scope that is representing the container, which is at the very end of this graph. So it's like a leaf on this graph. I put containerd or Docker. It depends on the container runtime that you use. The name will change. But anyway, if we zoom in this thing, because we are interested about memory, we will see that for memory. So a bunch of files. Some of them are read-only, some of them are write and read and only write. So the idea again is that the kernel will expose some statistics through these read-only files. And you can also again set a memory max, a memory min, some kind of boundaries to ask for the kernel to enforce those things for you. And the thing we are interested about is the memory current. So this is like the thing you've been seeing in the code just before. It's just a number. So this is pretty much the total of memory that is used by these cgroups. So all the process belonging to these cgroups. And you have this thing called memory stats, which contains much more details breakdown of all the memory usage. So you have the anonymous file kernel, which should like addition to this kind of total. And then you have like a lot of different statistics that you can use. So this is cgroup v2, by the way. They have 2 versions, but I try to focus on cgroup v2 in the next slides. And yeah, trying to make sense of the statistics you've been seeing before is actually a bit complicated, because memory is a bit complicated. Like, it has a lot of terminology. It is like a very complex subsystem into the Linux kernel. So today we are going to try to focus on just like a few words. So just trying to explain a little bit about like main memory, virtual memory, and overcommit. So main memory could be referred as like your physical memory, so the actually fast data storage memory inside of your computer, or the random access memory device on your computer. And then you have like the virtual memory. So virtual memory is this kind of abstraction that we built on top of the main memory, the physical memory. It is theoretically, it's like an infinite amount of memory, possibly. It doesn't need to pair with the main memory. And yeah, again, keep in mind that like virtual memory is not real memory. And that will explain like the difficulty to map to the physical memory. And the overcommit concept. So Linux, like the kernel, is overcommitting memory, which means that basically it will be able to accommodate for as much memory that you want to allocate. So if you want to allocate like 1 terabyte of memory and you only have like 8 gigabytes of physical memory in your computer, you can allocate that because Linux will overcommit. So how does that work? Let's try to see. So I borrowed this diagram from Brendan Gregg's Systems Performance book. Very nice book. And I will try to explain a little bit further this concept of virtual and main memory. Try to bear with me. So when you are writing programs and like running programs, you want to allocate objects, right? So if you are using C, it could be very explicit, like you just use malloc and you allocate like a new object. Or if you are using like a more modern language like, I don't know, like Go or I don't know, like Python, maybe you will not even realize that you are allocating memory. You will just like create new objects, and they will be there. They will be allocated on the heap for you by the runtime, but you might not even realize. But anyway, once you allocate that memory, it's actually taking no space in the main memory initially when it's completely empty. So you can allocate like terabytes and terabytes of objects. But as soon as you will start to store in this memory, so as soon as you will start to use this memory, behind your back, the OS, what it will do is that it will perform a lookup on this memory, la virtual memory. It will talk to this MMU thingy, which is the memory management unit. And if the memory is not actually backed by some physical memory, it will do something that we call the page fault. And it will ask like the MMU to map this virtual memory into some actual physical memory. So at this stage, like the fifth point, your memory will be like allocated and mapped. So it will actually, at this moment, it will like take some space on the physical memory. But just to show you like the complexity of this, like I mean, your object initially, it doesn't mean that your full object has been allocated in the physical memory. If your object is huge and the page size, so the minimum units of memory that Linux handle is smaller, you could have just like tried to rewrite on like some part of your object, and only like a part of your object could reside in actual physical memory. So even there, it's actually tricky. You've written to some object, you don't know if like everything has impacted your memory usage. And eventually, if the object that you are using, like the OS thinks that maybe this memory has not been accessed for a while and it's like under memory pressure, it might even decide to swap this memory. So to take the memory from the random access memory part, like the physical memory, and put it on some other device, like a slower device, like a swap device, like a disk. So from all the lifetime, you don't really know when it's like impacting the physical memory. It's always like an approximation. And just to add on top of that, on like accounting memory to process, memory can be shared between process if you are using like shared libraries. Memory can be compressed. So what it means is that you will need at some point to kind of create some kind of heuristic around your memory and try to stick with it, right? So this is what we ended up with the cAdvisor thingy. It was using this memory current thingy, or usage in byte for v1, and it was subtracting this inactive file thing. So as I said just before, the total memory is like separated into like anonymous memory, so typically a heap memory use in your program, like allocating objects on the heap, some files. It could be files that you used for I/O, like you've been like opening a file at some point and reading from it, and kernel, which could be like object related to your process running on the OS, like kernel stack or other things. But the thing is, like some part of, for example, the file breakdown of this memory, it could be inactive. So if, for example, your process opens some file at the beginning of its lifetime, it reads from it and never touches that file again, you might not need that like file to be in cache forever, right? So you could just like reclaim that memory later on. And this is kind of the idea of this number, like trying to take into account this memory that can be reclaimed before it's actually reclaimed. Because eventually what will happen is that when the out-of-memory killer will try to find more memory, or before it's actually called, it will try to reclaim as much as memory as it can. So it will try to reclaim all the memory from the cached file that are no longer used. So this is kind of the key takeaway 4. So this container memory working set bytes we have been looking since the beginning. It's actually the current memory use, like the main memory metric from the cgroup minus the inactive file. And it's like a kind of a good enough heuristic for the actual memory use and what the OOM killer is after. And I hope now you kind of understand why we need like this kind of good enough heuristic. So this is kind of the conclusion, like going from the physical to Prometheus again. So we have like this main memory. It's impacted by the objects that have been like allocated on the heap, the files that have been cached, the kernel files, the kernel structures that have been allocated, or even like or even more, but yeah, you have like this physical memory on the side, and the best you can do is using like this memory current stat from the C group. So this is like an accounting of this thing. So again, anonymous memory, it can be things on the heap. Depending on your language, you might want to use different tooling to understand like how can I reduce like the heap usage on my thing. For Go, for example, you can like use like the go-mem-stat thingy, or you can use like you can trust like flame graphs on how the memory is used. The file, it will be like the file that you interacted with, so the I/O you've been doing, or just like the binary that has been started as a process that needs to be mapped in memory before starting. And the kernel, it will be, like as I said, kernel structure related to the execution of your process, or in the case of Tetragon, it could, because we are using like this BPF thing, so BPF like is a kernel technology, and BPF procs, they use this thing called BPF maps, and the BPF maps for cgroup v2 are accounted, like the memory impact of those are accounted in the kernel box here. So all of these compose your container, then it's read by cAdvisor, like libcontainer, then cAdvisor that computes that thing, and it's exposed by kubelet, and then you retrieve that from Prometheus. So yeah, in kind of a conclusion, again, it's tracked by this thing, cAdvisor again, this is a heuristic, and this is what you're looking for. I just wanted to mention a bunch more things here. I found on the Kubernetes documentation some nice scripts. So if you are in a situation where you can't really like dive into the C groups and read everything by yourself and do the math by yourself, you can use these little scripts that they made to check like the main C groups and see like the working set bytes, the inactive files, and everything. And yeah, shameless plug. I did like a very small tool, so this is very limited. It's using libcontainer, like from runc again. And the goal here was just to kind of analyze my memory usage without having to start my full stack of like a Kubernetes cluster and everything. So this little utility, what it does is that you can give it your program, its argument, and it will start your process as a child, put it into like a C group, and monitor like the stats that come from this C group's memory stats. And the idea is to print it like regularly, a bit like simulating what we could do with Prometheus and Grafana, trying to see the evolution. So this is just like a very small utility, but can be helpful if you don't need to like spawn your own entire like Kubernetes cluster. So that's pretty much it for me. Thank you for joining. Sorry. I put some QR code on the thing. You can like go to see like the slides. I put the slides online. And yeah, thank you. Thank you for joining.